Okay, good afternoon, everyone, and thank you for coming to our WMG Steel Group Colloquium. It's my pleasure today to introduce Dr. Ed Pickering from University of Manchester. He's going to deliver a talk today. Ed is currently working as Senior Lecturer in the Department of Materials at the University of Manchester. And his research interests are mainly alloy design and characterization, microstructure, property correlations in steels, as well as in high entropy alloys. Ed completed his undergraduate degree as well as PhD, both from University of Cambridge. And after completing his PhD, he started his academic career as lecturer at University of Manchester from 2015. And currently he is now promoted to senior lecturer and also a research lead for advanced metals processing theme for Henry Royce Institute. Ed is going to talk today about the application of high entropy alloys for nuclear reactors. And thank you, Ed, for taking time and accepting our invitation. And stage is yours now.
Thank you very much, Prakash. Thank you very much for the invitation and to everybody at WMG for hosting me. Let me just pick the right window to share, and then we'll get cracking.
Yeah.
Is that okay? Can you see that all right?
Yeah. Yeah.
Brilliant. Okay, so yeah, thanks very much again for having me. I'm going to talk to you today not about any of my steels work, which probably most of you are already quite familiar with some of the themes that in my steels research. I thought I'd talk to you about something that might be a little bit different and new to people, which is about high-entropy alloys, and specifically the properties of high-entropy alloys for nuclear applications. This is the presentation structure. So I'm actually going to begin by talking about high-entropy alloys generally, so a general introduction to high-entropy alloys, and we're going to talk about something called the 4 core effects that exist in high-entropy alloys, or are supposed to exist in high-entropy alloys. And then I'll talk about high-entropy alloys for nuclear, motivation, asking whether they possess special irradiation properties, talking about how the design considerations we have for nuclear before talking about my group's own research, which is on low activation vanadium-based body-centered cubic high-entropy alloys, before summarising. So a lot of the stuff to begin with, I should say, is work. I'm going to refer to work in the literature as well as some of my own work, and then at the end there I'll talk very specifically about my own group's work. And so this is obviously isn't my own work. This is work that I've collaborated with lots of different people from the University of Cambridge, from Sheffield, Oxford, and yeah, here are some postdocs and PhD students who have carried out some of the investigations and the results that you're going to see. So high-entropy alloys. What are high-entropy alloys? So high-entropy alloys are alloys with multiple principal alloying elements. Typically, we have 5 or more of these alloying elements, and they're very often in near-equiatomic ratios. So the one definition is that there has to be at least 5 atomic percent of each alloying element, but so it's between 5 and 35 atomic percent of each alloying element. But actually, usually, very often you find that they're in equiatomic ratios, and that's just the alloys that we've looked at. So in other words, so they're called high-entropy alloys because if they happen to form solid solutions, they should have very high entropies of mixing. Okay, so high configurational entropies of mixing. So I mentioned just now that some of the most commonly studied high-entropy alloys are equiatomic alloys, and this one at the top here is an alloy called referred to often as Cantor's alloy, that was first studied by Brian Cantor, as many of you will know, and so this is just 20 atomic percent of each of the elements reading across the top row of the transition metals. Okay, and there are another couple of other common high-entropy alloys. Just to give you some background on the publications, the numbers of publications of high-entropy alloys continues to rise dramatically. So if I did a scope of search in August for super alloy and for high-entropy alloy, and you can see here that last year, actually, the number of papers that had high-entropy alloy in the title surpassed super alloy. for the first time, and now they're actually well ahead, and this was in August, and I can imagine this gap has grown, and we're probably aiming for over 3,000 publications this year on high-entropy alloys. So it's really has become quite a hot topic in metallurgy. And high-entropy alloys are and their compositions are supposed to give rise to special effects, and there are 4 of these effects, and they're referred to as the core effects, and they are that the solid solutions should be entropically stabilized, that they should have severely distorted lattices because we've got lots of different atoms of different sizes. They should have sluggish diffusion kinetics due to differences in atomic environment as we move through the lattice. And there's also another effect called the cocktail effect that is referred to, is essentially something to do with the unusual properties from complex composition, so unusual combination of elements. And what I'm going to do at the start of this presentation is just go through and talk about each of these effects in turn and about the evidence for them. So if we talk about entropic stabilization to begin with, we're hopefully many of you are familiar with the idea of configurational entropy of mixing. If I have a pure substance on the left-hand side here, the configurational entropy of mixing is essentially 0 because the number of ways, unique ways in which I can arrange that system is 0. It is 1, so it's and we log that and we get 0. And as soon as I start adding atoms into that system, I increase the configurational entropy of mixing. And the idea is that if I have a higher configurational entropy of mixing, so I have a higher entropy term here, that means that the solid solution that is formed has therefore a lower Gibbs free energy term. Okay. And the most extreme cases where we, or some examples of extreme cases are where we add 5 elements each at 20%, at 20 atomic percent, and we generate quite high entropies of mixing then. And the idea is that the Gibbs free energy that you reduction that you get from that increase in entropy outweighs the driving force to form intermetallic compounds. So actually, in high-entropy alloys, the idea of we shove more elements in, the random solid solution should be more stable or should be stabilized relative to intermetallic compound formation. Okay, so that's the entropic stabilization idea. So just in words, then this should outweigh the driving force to form detrimental intermetallic phases, and therefore we should find many high-entropy alloys with simple solid solution structures. Okay. And initial investigations of high-entropy alloys sort of supported this idea, but more recent studies have basically indicate that actually it's fairly rare that we find high-entropy alloy solid solutions that are stable across a full range of temperature. So really quite a classic example of this now is in fact the Cantor's alloy, and this is stable as a face-centered cubic solid solution at high temperature, which is actually quite a noteworthy thing, right? Because most of these elements don't form face-centered cubic structure at room temperature, but they do when you mix them all together at high temperature, and so you get a lovely homogeneous mixture of atoms like that, and a nice solid solution structure like, that looks like that. But if you actually age these at lower temperatures, you start to form other phases. So this is a sigma phase that, for instance, forms, and at lower temperatures, still you can form BCC chromium, for instance, and some other phases. Okay, so actually the evidence for the entropic stabilization effect isn't particularly strong. So there are very few 5-component high-entropy alloys that are stable to intermetallic formation. But there are perhaps some quaternary alloys that are stable. So if you take out the manganese, that might be a stable system. But many common alloying additions, like all these elements, because of their size difference and because of the enthalpy, they usually lead to some sort of decomposition. Okay, so high-entropy alloys still, unfortunately, or fortunately, depending on whether you look at it, still follow the Hume-Rothery rules, and enthalpy still dominates their microstructures in general. So that's entropy stabilization, let's move on to the severely distorted lattices. So the idea here is that due to the size mismatch of elements, we have, and this is exaggerated here, obviously, we have a lattice that looks like this. So it's a locally distorted lattice because of the change in atomic environment. Now, this sort of a distortion doesn't broaden X-ray diffraction peaks like dislocation do. Instead, it essentially increases the amount of incoherent scattering and damping associated with that, and it reduces the peak intensity, a bit like temperature does, really. Okay, and yeah, so I've been very fortunate to work to be associated with some work that's trying to probe this sort of lattice idea in high entropy alloys. So what a very good measure of this is something called a pair distribution function, where essentially we measure the distances to our nearest neighbours in our structure, and the width of these peaks essentially tells us how much distortion there is within the structure. Okay, some much more clever people than I am. So an example of that would be Lewis Owen, who's now at the University of Sheffield. Essentially, they do neutron diffraction measurements, total scattering measurements like this, Fourier transform that, and then they generate pair distribution functions that can then be compared with various models. And you can see here that if we compare the widths of these peaks, you might be able to convince yourself, okay, that the high entropy alloy does have a greater peak width here. However, when you account for things like the fact that the melting point will increase in this direction, so will decrease down here. So in other words, this is going to have greater thermal vibrations going on in the structure. The effect really is not a strong one. Okay, and the problem is that you might think, well, okay, this obviously won't be an example of a severely distorted alloy because all these elements are next to each other. That's true. Unfortunately, when you try and make a system which should have a lot of distortion, it then becomes more tricky to measure because often you have phase decomposition then. Anyway, if you're interested in this, I do recommend these two reviews by Lewis and Nick Jones. Lewis, as I said now, is at the University of Sheffield, and there are these two reviews that I do recommend you having a look at, and all the references are actually in the list at the end of my presentation here. They say, to quote them, there remains very little experimental data related to the level of local distortion in high entropy alloys, and that the metallurgical community does not have a good quantitative appreciation of the magnitude of alloying related to atomic displacements in any system. So actually, there's a lot of work to be done here. Okay, so that's severely distorted lattices. There's not very much evidence for them at the moment, but then there is still lots of work to do. So what about this third one? This is sluggish diffusion. So the idea here is due to variations in lattice potential energy, rather than surfing through a constant potential landscape, as would be expected in a pure substance, instead we've got areas where the atoms might become trapped, and that should give us sluggish diffusion. Well, if we look at quite a few high entropy alloys, and we look at their aging response as an indication of how fast diffusion might be, we actually find that, well, this is within 6 minutes at 900 degrees C, we're in an hour, and then 10 hours, we see that, yeah, diffusion isn't ridiculously slow, certainly in comparison to what we see in lots of nickel alloys, okay, here in the development of microstructure. And actually, people who've done proper diffusion calculations and diffusion studies, so this, I don't know whether this is, the surname here is Dobrova, but anyway, this is a great paper that talks about the state of a lot of diffusion studies in high-entropy alloys, and they conclude that based on literature analysis, it can be stated there is no experimental evidence which would support the existence of a sluggish diffusion effect. Nevertheless, it can be pointed out that our current state of knowledge in diffusion of HEAs is far from complete. Okay, so it's a similar effect. It's a similar sort of story to the lattice distortion business. What about the cocktail effect then? Well, this is a tricky one. It's supposedly the overall effect from composition, structure, and microstructure, but it's difficult to work out whether when people talk about this, it's any different to really what you find in standard concentration alloys like superalloys or austenitic stainless steels. Yeah, it's the idea that the complexities of high-entropy alloys compositions give rise to unusual properties, and sometimes they do. We'll talk about that later. But is this particularly special to high-entropy alloys? That remains to be debated. Okay, so in summary, this was sort of a whistle-stop tour through a general introduction to high-entropy alloys. I would certainly say, and this is, I guess, my opinion rather than anything else, and if you're interested in this, there's this review down here that I wrote with Nick Jones in 2016 that talks a little bit about this. There's limited evidence that the four core effects play a significant role in determining high-entropy alloys properties. This certainly seems to be true in terms of there being universal application to all high-entropy alloys. So I can't say that all high-entropy alloys have sluggish diffusion, because that certainly isn't the case. Okay. That said, though, there's still plenty of work to do. There's on lattice distortion, diffusion, etc. And I'm about to talk about the fact that there's still great opportunities to study high-entropy alloys, despite the fact that these core effects may not be so strong. Okay, so yeah, on the basis of that, as I was just alluding to, you might ask, well, why bother with high-entropy alloys at all? Okay, well, I would argue that, and lots of them in the community still argue that they represent an exciting opportunity for alloy development and enhancing our understanding, particularly of solid solutions, concentrated solid solutions. There is enormous unexplored space for us to design alloys in, and the alloy development is still worthwhile regardless of the influence of the core effects. Okay, so there are still certain applications, and we're about to talk about a set of applications where it's still worthwhile pursuing them, despite the fact that they might not all have sluggish diffusion, for instance. Okay. I'm not going to talk today about mechanical properties of high-entropy alloys in great detail, but just to mention that there are certain high-entropy alloys and related systems that have really shown exceptional properties. Okay, so this is the Cantor's alloy over here, and this has been tested at room temperature and all the way down to liquid nitrogen temperature here. And unusually, in an alloy system, the strength and the ductility both increase as you drop the temperature. And in fact, if you take manganese and iron out of this system, okay, it becomes less of a high-entropy alloy then, but this is what it's been derived from this work. You actually find that you get even better properties, and these are, I think, to my knowledge, the toughest materials that have toughest alloys, at least, that have been measured at cryogenic temperatures. Okay, so you can get similar behavior to this in terms of an increase in UTS and ductility with a drop in temperature in some austenitic steels and other austenitic alloys, but this particular the strength of this behavior, if you like, is particularly exceptional in these high-entropy alloy derived systems. So yeah, there are, even if these don't necessarily display lattice distortion, for instance, they do display some very other interesting properties. Okay, I'd like to argue that, and like many others do, that the development of high-entropy alloys is likely to be most beneficial for applications where our current alloys don't limit us. So we're not going to displace, we're not going to ever be able to generate high-entropy alloys that displace steels or aluminium alloys in automotive applications, or steels in structural applications, etc., because on a cost basis, we're just never going to, they're just, high-entropy alloys make no sense at all. So a cost and property basis there, and the specific property basis, they make no sense. However, there are some applications, such as maybe high temperature gas turbine applications, where they do make sense. And my particular interest is around fission and fusion applications. So these are next generation nuclear applications where the environment is very severe, and there's a question mark about whether our current set of alloys can work in these in such applications. So if you're interested in this, here's another review that I wrote with a number of co-workers here on specifically nuclear applications of high-entropy alloys. And I'm just going to summarize some of the findings in the next few slides. Okay. So if we look at the current candidates for fusion materials, so plasma-facing materials that go inside a fusion reactor, we see that we have quite a few materials here that are that seem to span a decent temperature range, okay, and they tend to be limited by irradiation brittlement, low temperature, and maybe creep at high temperature, for instance. And you might think, oh, great, you know, we've got all the materials that we need here. The problem is that to make a lot of these materials, so for instance, oxide dispersion strengths and steels in large quantities is really difficult, and we've been trying for a long time. So there are lots, and it's not just that might be the problem with the ODS steels. In other cases, there are other problems that mean that none of these alloys is quite perfect when it, certainly not perfect when it comes to fusion applications, and they might just not work. They might work, but they might not work, and we might not be able to make, for instance, enough tonnage of them to even implement them in a fusion reactor. So there are some gaps here for producing high-entropy alloys. Okay. Now, what I'm going to talk about in the following slides does involve a little bit of discussion about what irradiation damage is, or about irradiation damage defects in the formation of them. So I'm just going to outline that for those of you who haven't studied radiation damage before. I certainly hadn't before, you know, 3 or 4 years ago. So in a very, very basic way that probably will make some radiation damage people cringe, I'm going to explain irradiation damage. What generally we have is some sort of energetic particle. The energetic particle is in red here, and that comes in and hits an atom within our structure, and that creates a vacancy in interstitial pairs, and these are Frenkel defects. So we create lots of vacancies in interstitials. Now, that actually isn't what happened when we bombard an energetic particle. And what tends to happen is something like this. So if I just play this for you, we have an energetic particle coming in, that then hits and knocks on a particle, that then hits and knocks on a load of other particles, etc., until we have what's called the displacement cascade. And this is, I should acknowledge Bartek here at Manchester, who's given me this animation of one of his simulations. And we see that what we generate is voids. They're not immediately obvious here because we've got a number of they're not voids, sorry, I mean vacancies. So we have a number of vacancies here. So vacant sites, they're not immediately obvious because we've actually got a number of atomic layers on top of each other here. And we can also see some interstitial atoms here in green. Okay. And essentially what happens is that as these interstitial atoms and these vacancies, depending on the temperature and the various other conditions, they move around and they can form things like voids if vacancies agglomerate together, or dislocation loops. And these dislocation loops can actually happen when vacancies and or interstitial atoms combine with each other. Okay, and obviously these are going to change the properties of the material. Okay, so that's a very basic idea of what how irradiation damage works. So a number of people in the past few years have been asking the question, do high-entropy alloys possess special irradiation properties? So do they possess properties that are more special than other conventional alloys? And there are some studies that have found that high-entropy alloys show superior resistance to irradiation defect formation. So, for instance, in face-entropy high-entropy alloys, they form smaller but more numerous dislocation loops or reduced void swelling. And here's an example of that here. So we see that when we irradiate nickel versus when we add in more elements, we see the amount of voiding and the void swelling goes down significantly. Okay, so that's a very very interesting result. Other things, we found that some high-entropy alloys undergo significantly less irradiation hardening, so the hardening from all the defects that are formed. So, for instance, if we look at this is the irradiated versus the unirradiated state here. We can see that there's an increase in vanadium, but less of an increase in some of these concentrated alloys. So that's an interesting observation. Other things, and there's also been some claims, and there are some studies that demonstrate this, that some high-entropy alloys possess excellent phase stability as well under irradiation. So we irradiate them at temperature and they don't seem to decompose as readily as other alloys. Okay. The problem is that certainly we can't talk about this again in general terms, because not all the studies confirm these trends. Okay, so some studies, for instance, have found that they aren't stable. They don't show great stability, phase stability when irradiated. Okay, and in general, there is much more work that is needed, and there's not a huge amount of work out there. If we look at the percentage of studies that or the fraction of studies that might be focusing on nuclear out there, of those 3,000 papers, maybe there's like 50 published a year, 50 to 100 published a year that are actually on nuclear nuclear applications for high-entropy alloys. So it's still quite very much an upcoming field. In general, though, what appears to be the case so far is that things appear to be system dependent rather than universal to all high-entropy alloys. So we can't say that all of them are radiation resistant. Instead, certain systems may be. Okay, and there's also a question about whether they're actually any different to conventional concentrated alloys. There's been a huge amount of work done in the past on austenitic steels, for nuclear applications, and are they actually any different to those steels? Now, if you are interested in particular the FCC high-entropy alloys, I can recommend this review by Zhang, Armstrong, and Grant from the University of Oxford that talks about this irradiation in these Cantor-like alloys in a bit more detail. Okay. The final thing to say about these special irradiation properties is that many of the studies that talk about special irradiation properties refer to those same 4 core effects I've just talked about. And as we've seen, the universal significance of these effects remains disputed. So you'd expect that maybe if you have sluggish diffusion, that might inhibit void formation and growth, for instance, in some circumstances, or may in fact increase it in some circumstances. But if that was true for all high-entropy alloys, then maybe they would have some sort of consistent radiation damage resilience or whatever. But that's not what we find in general so far. And I should also mention there's a brilliant review. I think it's about 90 pages long in Active Material of high-entropy alloys in general in 2017 by Dan Miracle and Alexenkov there, and that I also recommend having a look at. So that all sounds like I've just been very negative again, but I'm not at all, and I think there is still great promise in this area, and we can still ask the question, so are there any intrinsic characteristics that could instill damage resistance in high-entropy alloys? Well, I'll give you an example of one of them that could be fairly universal to lots of high-entropy alloys. High-entropy alloy source solutions tend to have many high concentrations of many elements. We know that's what high-entropy alloys are all about. But this means that, and this is good, sometimes a good thing, sometimes a bad thing, that they tend to have lower thermal conductivities. So the question is, so if they do have the lower thermal conductivities, does this mean that when we fire our neutron or proton in the material, we create that damage cascade? Does the energy and thermal energy gets concentrated in that cascade for a longer period of time over a smaller volume? That means there's more time for irradiation defects to recombine. So imagine if the overall thermal the overall thermal spike, if you like, associated with the cascade looked like that in a conventional alloy. When in a high-entropy alloy, do we get just a more localized displacement cascade? Is a thermal energy concentrated over a smaller volume, and does this help us in terms of providing chance for defect recombination? So that could be one example. It's also worth noting that many stainless steels, of course, and zirconium alloys have low thermal conductivity, so it remains to be seen whether they are any different to those sets of alloys. But certainly, it's generally true that high-entropy alloys have worse thermal conductivities than their more conventional counterparts. So does this give you an advantage? And there's a lot of work on here, and it's something that very much an area that I don't really understand very well, on short range orders. So there's a huge amount of work, and Lewis Owen and Sheffield and others are looking into this in high-entropy alloys. And yeah, so there's a question about can short range order effects help out, and are they unique to high-entropy alloys? And the jury is still very much out on that one. Okay, so I've just talked a little bit about the motivation for high-entropy alloys, and asking a question about whether they potentially possess any unique properties. And I want to go on and just talk about the design considerations very briefly. Okay, so there is some good news and some bad news when it comes to high-entropy alloy design. These are generally true. Regardless, some of these are true regardless of whether it's for nuclear or not. The good news for nuclear is specifically that we have some restrictions on our choice of elements that shrink our palette of elements. And I'll talk about this a bit later, but basically if you want to avoid lots of radioactive elements that become radioactive, that shrinks our elemental palette. Okay, so we might want to reduce activation, low neutron cross section, etc. The bad news, and this is true for all high-entropy alloys, is that modelling of high-entropy alloys remains a huge challenge if knowledge of the system is required beforehand, and this makes screening of alloys really problematic for any sort of application, and in particular for irradiation damage, because there we've got lots of complicated effects going on. And also another set of bad news, I mentioned before that ODS seals were difficult to make in bulks. Well, often high-entropy alloys are difficult to make in bulk too, particularly if you've got very different melting temperatures amongst the elements. Okay. And again, another great review on that I recommend if you are interested in design considerations for nuclear applications in general. HEAs, do check out this review here. Just to focus in on one specific other consideration, there's a question about whether we should use face center cubic or body center cubic alloys. So in some ways, this is sort of answered for us because many face center cubic forming elements are not favourable from an activation standpoint. So if you irradiate nickel and copper, cobalt, for instance, and copper as well, they can become very, very active, and this is not a good thing. And there's the general sort of underlying theory that face center cubic structures also form more voids and they swell more readily than their body center cubic counterparts, although that's certainly not always true. Oh, and there's a little bit change in formatting there. And so that's against the FCC. For the BCC, in terms of the BCC, then there are some BCC low activation elements to choose from. That's a good thing. They should, in theory, be more resistant to swelling, although actually the jury is still very much out on that front. I mean, if you have vanadium iron alloys, for instance, they've been shown to swell a lot. Problematically, though, they tend to be brittle. They tend to have poorer creep performance, so the same homologous temperature, and interstitials in body center cubic, in particular body center cubic refractory alloys, are a real problem. So yeah, hydrogen, carbon, etc., are a real problem. And just to illustrate the problem, many of the body center cubic alloys that you might think are suitable for nuclear applications are actually also being looked at for hydrogen storage as well. Okay, so for hydrogen storage, of course, this means that they store hydrogen and they also give it back out. So you should be able to spit the hydrogen back out again. But in general, if you're, for instance, in a fusion reactor and you've got lots of tritium and deuterium and all sorts of things flying around, and radioactive tritium and tritium that's quite precious for you to keep within the fuel cycle, then it's a problem that it gets locked up in your materials and probably embrittles those materials. So yeah, there are a huge number of considerations out there when it comes to nuclear, but it is still a big opportunity, and I've talked a lot about the limitations. Maybe that's just in my nature that but the compositional space of forward related by hydropel means there's lots to explore, and there are lots of unique opportunities to tune irradiation response.
How are you? Good. You okay?
Nice.
How was the
I think we've got some
trip
people.
to Iran?
Basically the High-Entropy, there's a big opportunity to tune their radiation response alongside other properties. So for instance, can we use compositional freedom to tune defect strengths and sink strengths and the strength of vacancy, agglomeration, all sorts of different things like that. Okay, so it still remains a big opportunity. Okay, so in the last 5 or 10 minutes, I'm just going to talk to you about my group's own research. We've mainly, when we've been looking at high-entropy alloys for fusion applications, been considered with plasma-facing components. So in particular, the first wall, the blanket, and the diverter that you see sort of at the centre of the tokamak here, the torus. And these sort of components are going to see really high damage rates. So this is 10 displacements per atom per full power year. So over the course of a year, every atom will get displaced from its site 10 times. That seems like a ridiculous amount of damage. And we want to, at the same time, we're bombarding them. We want to run them at hot, ideally at 800 degrees C, and they need to have low activation elements. So we can't use nickel superalloys because we don't want to use nickel. Okay, so the design philosophy that some of my students have adopted is sort of follows on from what we just discussed about face center cubic and body center cubic high-entropy alloys. We've used low activation elements. We've looked at body center cubic crystal structures, hopefully, so this means that we get a lower radiation swelling. We've looked at high melting point elements for good intrinsic creep properties. And we've also added elements like chromium for environmental resistance. And we targeted solid solutions to begin with, so elements that are compatible, we think are compatible with each other, in order to then introduce second phases for strength later on. So this is a really key and interesting periodic table. This is developed by Mark Gilbert and co-workers at UK AEA. And essentially it tells us the number of years here that it takes for an element to decay its radioactivity to reduce to low-level waste after it's seen a fusion plasma. Okay, for 14 years. Okay, so that might be, that's a decent amount of time that that's been exposed to a fusion plasma. And we see that some elements that are usually quite good elements for high strength applications like nickel, for instance, are just not going to cut it because they take. This takes 460,000 years. To decay to safe low-level waste, and part of the motivation for fusion is that we eliminate a lot of the long-lived radioactive waste. So we're actually, and this is a good thing for high-entropy alloys because otherwise we've got too many options. And we sort of limited our palette, and my group in particular has limited their palette to these elements here. And specifically, actually, I'm going to talk about the combining these elements up here to make lightweight high-entropy alloys. Other groups, and for instance, the group of Amy Gandhi at Sheffield and Dave Armstrong at Oxford, have looked at a lot of tungsten and tantalum containing high-entropy alloys as well. So we've explored these systems and we sort of built up our elemental palette from the unary system right the way to the quinary system, and looked at the effect of adding in these elements. Okay, so those first two, the unary and the binary, very well known stable solid solutions, so there's no problem with them. The chromium manganese, vanadium chromium manganese system appears to be as stable as a single phase solid solution across all temperatures. Okay, so when you add approximately equal amounts of those together, they seem to be all good. And some work by a student of mine called Paul Barron has demonstrated that. When you add in titanium to remove some of the interstitials that you often see getting caught up in when you make these alloys, you do successfully form sort of like titanium oxide, titanium carbonitrides, and that sort of stuff. And we find that actually, though, the amount of titanium we can add into the system is quite low, because before we form some horrible intermetallics, and so it's about up to 4% titanium into an equiatomic vanadium, chromium, manganese alloy, we can only put in a small amount of titanium before that becomes an issue. In another set of work, we looked at adding iron into the system. So again, building up the elemental palette to become high entropy alloy-like. And what we find in this particular system is that we form a single BCC phase at above 1000 degrees C. But as you might expect, given the combination of elements we get here, we've got here that we form a sigma phase extensively at lower temperatures. So there are a couple of publications by postdoc Alex on this subject. This, for instance, is this alloy, equiatomic alloy at 1000 degrees C, and this is at after 800 degrees C. And we can see that this looks like a lovely BCC solid solution almost entirely, and this looks there's lots of sigma phase that pops out here. Now, the interesting thing is that, so then Alex looked at adding in aluminium into this system for two reasons. Firstly, aluminium suppresses sigma phase, and you can suppress sigma phase at approximately more than 7% aluminium. And secondly, because aluminium forms B2, so these are sort of like ordered intermetallic phases, superlattice phases of the BCC solid solution. The aluminium forms these B2 and Heusler phase precipitates, and that's also a good thing for high temperature strength as well. And also, aluminium isn't bad for environmental resistance either. We found some really interesting microstructures here where we have coherent superlattices of superlattice phase B2 and Heusler phases precipitating within the BCC matrix, and yeah, there's still a huge amount of work to still continue with on this subject. We are currently doing some bulk mechanical properties, so we've actually made kilograms worth of ingots of this alloy, for instance. We're doing some bulk mechanical property and irradiation testing of these alloys. We foresee, though, that there will be some problems with interstitials and hydrogen retention and limited ductility in these alloys. So we'll have to see how we get on with that. Okay, so yeah, that's. I realise I've gone through things very, very quickly, so apologies for that. You'll have to watch the YouTube video and then slow me down by about a factor of half or something. Yeah, so in summary then, I've talked a little bit about high entropy alloys in general to begin with. I then talked about the fact that irradiation properties of high entropy alloys are likely to be as diverse as their compositions are. Just as is the case actually for mechanical properties, corrosion properties, etc. They still, however, represent an exciting opportunity for new for new alloy development for advanced nuclear applications. So, for instance, can we use that compositional freedom to tune irradiation responses? Possibly. There's still a lot more to do. Many more comparisons are needed to conventional alloys, for instance, and something that I didn't touch on so much was, but is worth highlighting, is that they're a vehicle to increase our general understanding of alloy properties and responses. And really, what I mean is concentrated alloys there, and concentrated solid solutions in particular. And the final thing I just want to say, because it would be I wouldn't be doing part of my job day to day if I didn't do this, is that just before we finish, I'd just like to highlight to everybody on the call that if you are in the UK, and I think even if you're outside the UK, that's fine too. There are lots of facilities that hopefully are mostly complementary, or a lot of them are complementary to the ones you have, the great facilities you have at WMG. Lots of facilities to access through the Royce Institute. Do check out the Royce website, royce.ac.uk for that. There are things like lots of additive manufacturing machines. There's a sheet forming press. There's a spark plasma sinterer. This is a strip caster, for instance. Lots of funding schemes for free access for that, and we're keen for everyone to use them. So if you are interested, check out the Royce website and drop an email to royce@sheffield.ac.uk. That's where a lot of the metal stuff is led out of. And yeah, so I think that's all I wanted to say on that front. So with that, I will finish, and there are all the references. If you're interested, you probably can't remember though. I mean, I'm not sure I can which slide corresponds to which, but there we go. So yeah, thank you very much. I'm happy to take any questions.
Thank you, Ed, for the wonderful talk, and I welcome any questions from audience. Any questions?
Yeah, I've got my
Okay.
hand up, Prakash.
Oh, okay. Hello, Carl.
Yeah, sorry.
Yeah.
Hi, Ed. How are you doing? You all right?
Hello, Carl. Yeah, please, please ask away.
I guess a general one, or two questions, if I might. And the first one's more of a general one about high-entropy alloys. How, obviously a lot of alloy design now has a lot of is starting to take into consideration recycling, and what you're talking about here with nuclear, I guess, is less of a problem because we're so worried about how radioactive it is rather than I guess there's something. But in other areas of HEAs, how responsible is it for us to be making hundreds of thousands of different alloys with these very high levels of different alloy additions? Because I think we're going to end up ourselves with it later down the road where we're going to be really struggling to recycle these. Again, it's probably unfair because you're focusing on nuclear, which is probably the one that is probably less of a worry.
No, but yeah. So to answer that question, it's a great question, and you're absolutely right. It is. If you're looking at an environmental sustainable, in terms of their recyclability, their life cycle, it's a difficult case to make for lots of high-entropy alloys. They often comprise elements that are expensive, that come from areas of the world that you don't necessarily want to. So the supply chain, there's ethical supply chain issues around a lot of elements that end up in high-entropy alloys as well. It's a really key aspect. I know that Brian Cantor is doing some work in this area at Brunel, and perhaps Professor Fan can comment on this, in the circular metals centre hub that they've got down there. So it is very much something that is being looked at. But yeah, it's a real problem. It's a real problem for the high-entropy alloys. I mean, people might say, oh, we're doing them for green applications, and we're going to make things stronger, and therefore we use less of them. But if you look at the amount of alloying element we've got here, it's a real concern, and they might be difficult to produce, and they're even more difficult probably to recycle. Perhaps maybe if we incorporate them into other streams sensibly, like stainless steel waste streams, they might be sort of complementary as master alloys, or as in highly concentrated alloys in that respect. But we've got to be really, really careful about that and about the recyclability of them for sure.
Yeah, absolutely. And I think it's just, and I think once the like you said, the rate of all these publications for HEAs is going really up faster than the number of applications we're finding for it. So I think once the market finds out where the sustainable use of HEAs becomes, I guess it becomes more of a question then. My second question, if I may, again, is possibly a slightly cheeky one. Most of the HEAs that I see are of these quite expensive alloys. Is there a HEA equivalent of something of all the really cheap stuff that we can get our hands on? And from a recycling point of view, is there an alloy that you can make that actually, of all the stuff that is really hard to recycle, because it's some of the aluminium alloys where you put it in and you just can't recycle it anymore? Is there a HEA where it could be all the end of life and the stuff that can't be turned into anything else that's useful? Is there one that you can a HEA you can turn into that? I don't know.
That's a really, I think I may have heard someone else talk about that before. But the idea of like taking all the stuff you can't recycle normally and just creating HEAs with it is a really interesting idea. A really interesting idea. Nothing really springs to mind in terms of like an high-entropy alloy that is cheap. I can't think of one really, because nothing's cheaper than iron in general, or as soon as you start adding elements in, and adding more elements in, you tend to just add in more expensive elements to things. Yeah. So that's a key issue. But but that idea of sort of being able to create high-entropy alloys with scrap, unrecyclable scrap from other streams might be a really interesting one. You should probably publish on that now, Carl, otherwise there'll be a paper on that next week. So
I'll have a look. But yeah, I guess it's similar to like using all your pantry, you know, when you've got you're just using all the less rather than having to buy expensive ingredients in. Anyway, thank you very much. I really enjoyed that talk.
Thanks, Carl. Yeah, Claire.
Yeah, perhaps I can follow that up. That, you know, one of the things that you didn't comment on, so I'm hoping you can comment on, is what the sensitivity to composition is. So reality, when you make things, it's never spot on what you aim for. So how much sensitivity is? You mentioned a little bit about, say, some of the pickup elements
yes.
and your concerns with some of the interstitials or things like that. But even sensitivity to your aim composition. What's that for these materials?
Yeah, so that's a great question, Claire, and in fact this is a sort of a very much something that the community is a concern for the high-entropy alloy community in general, in terms of the reproducibility of results based on nominal compositions. I think it depends what we're, and this is saying sound like a cop-out, but it depends. It depends on the alloy system and what we're looking at. If you look at what we're specifically we're measuring, so if you've got like the Cantor's alloy, for instance, small changes in the amounts of chromium, manganese, iron, cobalt, nickel in that system, let's say plus or minus two atomic percent, don't seem to change the results all that much. Some people have done some work on that, and so certainly the thermodynamic database predictions that have been done don't suggest that there's a great deal of change in terms of the phases you see and that sort of stuff if you look at that. But there are, so that's an example where there doesn't seem to be a huge amount of change. But there are examples, and the interstitial one that you stated there is a real critical one, where people have measured the properties of refractory high-entropy alloys and come up with different answers, okay, of nominally the same compositions, and this is almost certainly due to changes in interstitial concentration. And yeah, so in particular for refractory high-entropy alloys, there is still, in my opinion anyway, there is still and this, you can see some of this in literature, there is a big question mark over you know, what are you actually measuring here? Have you measured the interstitial concentration, and is this impacting all your other properties? I know that Dave Armstrong at Oxford has done some historic work where he's looked at the effect of nitrogen pickup, for instance, in some of these alloys, and you can form totally different phases just based on quite small amounts of nitrogen. And if you're not careful, you would think that they are not nitrides, but they're some other phase if you haven't measured the nitrogen. So yeah, it becomes really tricky, actually, in particular with those refractory alloys. So there's some alloys that seem to be a little bit that they don't mind so much, but then when it comes to other alloys, it's a real problem. Yeah.
My sort of follow-up question is, because there are lots of issues about being able to make these in bulk, being able to have things that are reproducible on a large-scale basis.
Yes.
What, in your opinion, if you had to, I know this is an unfair question, but if you have to, what do you think the timescale is for any of these alloys actually making it into a bulk practical application? If at all. And I don't think there's any problem with saying it may never get there, because there's a lot of learning that can happen anyway, although one hopes that it's appropriate learning. But you know, if you had to put your money on it, what would you think?
Yeah, good. That's a really good question. So there are sets of high-entropy alloys that are already in application. You can already buy off a website for brazing, but that's not bulk. So that's nowhere near bulk, in fact. Yeah. It's a really difficult. It's a very difficult question. It seems like, you know, with some of these alloys, the ones that are approaching like nickel alloys and stainless steels, they're not. You can see, it is apparent you can make them in relatively easily in bulk quantities. But I don't mean nobody's made tons of them. Yeah. Kilograms of them. Okay. And they seem to work okay there. But when we're talking about the sort of the high temperature applications, which is I think the high temperature and extreme environment applications that I think that ultimately we'll see applications in, right? The really extreme environment applications are going to be really the only applications where we're going to see them in. The alloys that you tend to use in those more extreme applications are more difficult to make in bulk. And so I think we're at least, I mean, if I want to, I'd say we're at least 10 years away from using anything in those applications, because they tend to involve some really, really nasty elements.
So if I ask the critical question, that considering the UK strategy for nuclear and the timescales that are required to define the materials before you even start design and build,
yes,
would I be fair in saying that it's highly unlikely, if not downright impossible, that the high entropy alloys will be ready for this generation of new build nuclear?
That's absolutely correct. Yeah, and there's no chance they'll ever. Well, even some great steels that have been around for decades, they're not even going to find their way into the generation 3, so the standard fission reactors. I also don't think, as you might say, that they're going to find their way. There's no chance they're going to find their way into the first generation 4 and fusion reactors. They won't do that, and that's sort of in the 2030s. They'll only find their way probably into the generation after that, or maybe they'll find their way into some of those first reactors as test components, right? But they won't find their way into widespread application. You're absolutely correct. Yeah, certainly it's the opinion I share until that second generation. We're talking like 2040s there. What might force things along a bit faster is if we try to build the reactors out of the current, like if we build the STEP reactor, for instance, the UK's fusion reactor out of our current set of alloys, and they just flat don't work and they immediately fail within like 2 months. That would then maybe really force a lot of these more exotic materials into those applications faster. But I still, it's still not going to be in the 2030s. I don't think.
And then a last question for you, Ed. We're a big steel group, and so we're passionate about steels.
Yes.
You have a background in steel.
Yes.
What learning can you take from the work that you do on high entropy alloys, and can you bring that back into the steel community to provide even better steels? So we have that cross learning between them. And so are there things that you can take out of that work and bring back into the steel community to get an impact? So not saying one's better than the other, I don't mean that, but it's really about taking that learning to try and provide impact sooner in the steel community.
Yes, yeah, so that's a great question. So I mean, at heart, I am still a steel metallurgist, right? And I sort of do high-entropy alloys as this novel thing on the side. But I think that there is some learning and some benefit to be had in the concentrated alloy end of the steels, and I'll talk about maybe two examples of where I think it's beneficial. Firstly, high entropy alloys have had to, and this one isn't really about learning, but it's more about like about other things, enabling research, and that is that a lot of the high entropy alloy work has forced thermodynamic database providers to really assess much more rigorously their binary, ternary, and quaternary systems in a way that they haven't been asked to before. And I think that's only a good thing if we're looking at developing like really exotic, high temperature, high strength power plant concentrated steels, for instance. You know, if we're going to introduce all sorts of crazy sort of precipitates and we're going to alloy them a lot, or maybe we're introducing some new TWIP steels, or you know, or something like this, I think it's only a good thing that the thermodynamic databases are being more rigorously tested by the high-entropy alloy community, and that has been fed through into steels. So that's the first thing I'll say. And the second thing, there's a lot of work that's been done on but I've not done this myself, but on the mechanical properties of high-entropy alloys, and I show some graphs at the start of those exceptional high-entropy, exceptional cryogenic properties from FCC high-entropy alloys. And a lot of that work based on like altering stacking fault energy and introducing Martin-Sittig transformations or introducing twinning. A lot of that has been led by Dirk Rabe in Germany. That does have direct read across into some, again, only some concentrated steels, but it does still have a direct read across into those, like the TWIP type steels, and yeah, those sort of steels where they're quite highly alloyed, that we are messing around with, if you like, for want of a better phrase, in that space. Can I think of any examples with respect to, like, you know, our good old exceptionally useful low alloy steels, high strength low alloy steels? I think that's more maybe more tricky. Maybe there'll be something in the, like, the interstitial space that'll come across there. I don't know, but yeah. So from what I can think of right now, it would be more towards the concentrated steels that maybe there's some read across and some benefit there.
Super. Thanks ever so much.
Cool. Thank you very much.
Suresh, are you there? Your questions? I think he left.
Oh yeah, we are over 2 o'clock now, so apologies for that.
Oh, okay. There are a couple of questions by Suresh Babu. You can see in the chat.
Okay, wait.
He says, are there...
Stop sharing my, and then I'll have a look at the chat. Sorry. All right. Yeah. Are there any differences in electromagnetic properties of the alloys if they are single phase? Yeah, so there is quite a lot of work. I've not really read very much of it at all regarding electromagnetic properties, because you can, you know, if we take like antiferromagnetic chromium and ferromagnetic iron, and we mix them together, and lots of the elements that they end up mixing together have very strange or very interesting magnetic properties. And then when you combine them together, what then happens is a real is very much an area of work. I can't really comment on that too much because I've not really read very much on it. I do know that lots of papers say that you should take into account there's a magnetic contribution to the entropy, and you really need to account for this in when you're working with high entropy alloys. Are the hardness
Are the hardness differences in the irradiated materials due to local phase change, or purely due to change in vacancy or self-interstitial concentrations?
That's a good question. You can get hardness changes for a number of different reasons, and when you irradiate these alloys, so you can change the phase, just as Suresh has said there. So you can change the phase. You can introduce, you can get more and more carbides or nitrides or any other precipitating phase. You can end up precipitating more of that, and that can be accelerated due to increased diffusion because you've got more vacancies around and all sorts of things. You can also get it's like classic irradiation, hardening, irradiation, embrittlement. It's because you introduce more dislocations, because you introduce these interstitial atoms that then form dislocation loops, and that sort of stuff. So it's a combination of all those things that he's mentioned there, really.
Okay. Ed, we have one more question from Jackie. Can you quickly go ahead?
Yes, thanks, Ed. I'm Jiaqi from WMG. I'm research fellow. I got a question for you. So during your presentation, you seem like to challenge the core effects of the high-entropy alloy. And you also claim that maybe BCC does not necessarily have higher swelling resistance to FCC. So when you design your BCC high-entropy alloy for nucleation application, what's your theory? Then what's your theory that can support your design?
Yeah, that's a good question. So it's mainly the the elements, you know, I showed that periodic table of elements. There's that
Yeah.
periodic table of elements, and actually when you look at the FCC elements, they are just not suitable full stop because they get too activated. So if you look at things like cobalt and nickel, they're just absolutely out of the question because for nuclear applications, because they become too radioactive. So
Yes.
it's almost, I'm not absolutely sure that BCC is the way forwards, but you can't really go to FCC because of the limited number of elements. There are some other FCC elements, some of the precious metals are FCC, but then there's a real problem around cost then. So yeah, it's more out of, I've gone BCC more out of hope and out of necessity rather than absolute belief that they're the right thing to do.
Okay, so when you choose the BCC, it's because it's less active, and yeah, we don't know how resistant to irradiations it will be. We still know yet. Even compared to the stainless steel or the mature steel you present. Okay, another question. Sorry, very quick. So as we discussed, so in terms of publication, you see very huge amount of publication about high-entropy load. But what's the problems or hurdles for massive production of high-entropy load, and compared to those steels, I know high-entropy load could also have some not necessarily better. For example, oxidation coefficients, oxidation resistance. It's especially when you apply to a high temperature severe environment, and also the corrosion resistance could be worse than our steels. So do you have any comments on that? Are you still confident in the future of the high-entropy alloys?
Yeah, so it's I guess in terms of like statistics, you would think that given the number of possible alloys that could exist in that high-entropy alloys covers, right? It's not just steels. It's you've got, you know, a countless number of alloys that could be classed as high-entropy alloys. I'm still confident that they will find some sort of application at some point. I think that, but as I mentioned in answer to Claire's question, I think we are still decades probably away from that at the moment, or at least in some cases we're decades away from them. Maybe there are some applications, but I'm talking bulk structure applications that we're decades away from. But maybe there are some applications where they're much closer. I don't know. But you are right in that because we can add lots of things like chromium and aluminium into them. In theory, they should be able to give us very good environmental resistance. And there's lots of work on that, although I've not really read up very much on it.
Okay. Thank you very much. Thanks.
Thanks a lot. I don't see any more questions, and also it's quite a bit long time for you after already 10 minutes past. So once again, I take this opportunity to thank you, Ed, for your time and wonderful talk from our group side as well as from WMG. Thanks a lot.
Yeah, thank you very much, Prakash. Thank you very much.
Yeah.
Cool. Bye-bye.